We spent the last couple of days talking about standing waves. A couple of days ago, we did a little demonstration where we observed standing waves, what it looked like, more or less when it happened, how it happened, the idea of interference of waves at specific frequencies. Remember that standing waves occur at very specific frequencies that we call the resonant frequencies, the natural frequencies of the string or of the air column, as we saw yesterday. Everything has a natural frequency at which it wants to vibrate. The bridge that we saw the video on here a week or two ago, the meter stick that we flicked, okay, has a natural frequency at which it wants to vibrate. Everything has a natural resonant frequency at which it wants to vibrate, including the strings that we've used with standing waves and including the air columns that we analyzed yesterday with standing waves. So when do they occur? When do these natural or resonant frequencies occur? When do these standing waves occur? Well, yesterday we drew 3 sets of diagrams. The first set of diagrams was for a string that was attached at both ends, like a guitar string that's attached at both ends, like just about any string, the string that we used in the demonstration the other day that's attached at both ends. Odds are, if you're going to flick a string and get it vibrating, it's going to be attached at both ends. Well, when we do that, regardless of what the exact scenario is, when that string is attached at both ends and we give it a flick, it will vibrate at lots of different frequencies, hundreds or even thousands of different frequencies, but most of them disappear right away. The only ones that stick around, the resonant frequencies. The first resonant frequency that sticks around would look like this. Our first standing wave looks like this. The second one, as you guys saw in the demonstration, would look like this. Whoops. If we have one antinode in the first one, then we have 2 antinodes in the second one. The third one that we would see would look something like this, where we have 3 antinodes. Again, from the demonstration the other day, we knew that we started with 5 hertz, we cranked it up to 10 hertz, we get 2 antinodes. We cranked it up to 15 hertz, we get 3 antinodes, and so on and so on and so on. How exactly are we going to derive the equation that goes with this? Well, we're going to define the length of the string as L. And now we're going to define the length of the string in terms of the wavelength. So let's look at each of these scenarios here and tell me how much of a wave that really is. Just for reference, here's a wave. All right, so if we're going from here to here, okay, it's like we're going from here to here on this wave. How much of a wave is that? Is that a full wave? Is that a half a wave? Is that a quarter of a wave? What is it? It's a half a wave. So we're going to say L is equal to 1/2 of a wave. Or lambda is equal to 2L if we want to rearrange that. This one would be equal to a full wave, right? We're going from equilibrium through the crest, through the trough, back to equilibrium, okay, back to here. That's one complete wave. So we're going to say L is equal to lambda, or same thing as saying lambda is equal to L. Down here, this is 1.5 waves. One wave, another half. We're going to say L is, we're going to say call it 3/2 lambda, 1.5. We're going to rearrange that, say lambda is equal to 2/3 L. Now, we can derive the equation from this. The frequency that we would see or hear, if this is a musical instrument like a guitar, okay, the frequency that we would see or hear would be equal to V over lambda. That's the universal wave equation that we learned last week. Lambda we're going to replace with 2L. So it becomes F is equal to V over 2L. This is what we call the first harmonic. This is the first standing wave that will occur in that guitar string or in whatever string it is that's attached at both ends. The first standing wave that will occur. The speed of the wave divided by 2 times the length of the wave. Sorry, the length of the string. Now, what's the next one that occurs? Once again, we say V is equal to, or F is equal to V over lambda, but lambda is equal to L this time. Sub in L for lambda, and we get V over L. You take a look at the second one, it happens to be twice the value of the first one. So what are we going to call it? Second harmonic. That's why when we did our demonstration the other day, the first one happened at 5 hertz and the second one happened at 10 hertz. Twice the value of the first one. Third one, F is equal to V over lambda, but lambda is 2/3 L. We can simplify that a little bit and say F is equal to 3V over 2L, which is, sorry, this should be, yeah, 3V over 2L, which is 3 times the value of the first one. Therefore, we're going to call that one the third harmonic. So all these different harmonics that are produced in these strings that are attached at both ends. The first one, V over 2L. Second one, twice that value. The third one, 3 times that value. What did we say yesterday about all these different equations? What do we got to remember out of this? We got to remember or derive this equation for the first harmonic. Why do we not need to bother remembering or deriving these two equations? Yeah, go ahead. They're proportional, but not just proportional. They're specifically twice the value of the first one, 3 times the value of the first one. So if you're looking for the third harmonic and you've got the value of the first one, which you can do by using that first harmonic equation, then just take the value of the first harmonic and multiply it by 3. If you're looking for the third harmonic and you calculate the first one to be 200 hertz, then the third one must be 600 hertz. It's got to be 3 times the value of the first one. So this is important. All of this is important, but especially this equation is important. Whether you remember it or whether you derive it like we just did, it doesn't really matter. You need to know it. The next situation is when we had air columns. This is like going across the top of the water bottle. Remember the other day I was trying to do that? And working today. We hear a sound, right? We hear a frequency. We hear a pitch of a sound there. There's standing waves set up in that air column. But those standing waves we can't see like we did with the string the other day because air is essentially invisible. If we could see it, the first standing wave that would be set up would look something like this. It looks a lot different than the first standing wave set up over here. When we have a string that's attached at both ends, we have to have a node at the closed end or at the fixed end. But when we have an open end, this is like a pipe or a didgeridoo, where we have 2 open ends, and that means we have to have an antinode. So the first sound that we hear looks like this. If we could see it, it would look like this. Length is L. We're going to say that the length is 1/2 of a wave because we're going from crest down to trough. Lambda is equal to 2L. F is equal to V over lambda. We're going to sub in 2L. Isn't that the equation that we got over here for the first harmonic? It is. It's not a coincidence. When both ends are the same, if it's both ends attached like a string or both ends open like a didgeridoo, when both ends are the same, then the first harmonic is V over 2L. Now, can anybody explain to me, talked about this a little bit yesterday, can anybody explain to me why the sound that we hear out of a didgeridoo that's 1 meter long is different than the sound that we hear out of a guitar that has a string that's 1 meter long? What's the difference? If the equation is the same, V over 2L for the first harmonic, why do we not hear the first harmonic the same value? What do we know about the sound in the string as we pluck the guitar string versus the sound in the air as it resonates back and forth through the didgeridoo? It's a different frequency, but why? If the equation is the same, look, V over 2L for the didgeridoo, V over 2L for the guitar, why, if the length of this guitar is the same as the length of the didgeridoo, why don't we hear the same frequency? The materials are different, so what? No, because the equation is the same, right? V over 2L, regardless of whether it's attached at both ends like this or open at both ends like this. It is a different material, which has trying to lead you a little bit further with that. No, if the material is different, then yeah, but no, you guys are kind of dancing around this. If the material is different, then the speed of the wave is different. The speed of sound travels differently through a guitar than it does through air. In fact, it's a lot faster through a guitar string than it is through air. So even though we have the same equation for a guitar string, V over 2L first harmonic, versus a didgeridoo first harmonic, the speed of sound in the guitar is much greater. So if V is bigger, then the frequency is going to be bigger, right? You got a didgeridoo or a whatever instrument with two open ends that's the same length as your guitar string, the first harmonic will be dramatically lower pitched. And the reason it will be lower pitched is because the speed of the sound in air is smaller than it is in the guitar string. All right. By the way, there is a second harmonic. It's twice the value of the first one. The third harmonic, 3 times the value of the first one. We analyze it exactly the same way as the guitar, except the speed would be different, right? All right, last one. This is when we call this a closed air column. We have a closed air column. We have to have a node at the closed end, and we have to have an antinode at the open end. If we could see the air resonating back and forth, this is what it would look like. We can't, but if we could, this is what it would look like. We're going to say L is the length of the air column. This is like a pop bottle, right, or a water bottle. Okay, when I blow across the top of this water bottle, this is exactly what we're dealing with right now. One open end, one closed end at the bottom, right? We're going to say here L is equal to 1/4 of a wave this time, because we're going from equilibrium all the way up to crest. That's 1/4 of a wave. Lambda is equal to 4 times L. F is equal to V over lambda. Sub in 4L for that. F becomes equal to V over 4L. Look at this one. That's still the first harmonic, but the first harmonic produced when you blow across the top of a water bottle with one open end, one closed end, is a different value, even though the speed might be the same as it is for the didgeridoo. It's a different value of frequency because the equation is different. Now, what do we know about the next one that's produced? Yeah, if we keep deriving equations, there is no second harmonic for the closed air column, for one open, one closed air column. Rather, the third harmonic would be 3 times the value of the first. The fifth harmonic would be 5 times the value of the first, and so on. There are no even numbered harmonics here. When both ends are the same, there's first, second, third, fourth, fifth. When the ends are different, then there's just first, third, fifth, seventh, so on. All right? Yesterday we gave you a worksheet, 2 sides to that worksheet. We'll let you work on the first side of the worksheet in class. We gave you the second side for homework.